This is part 4 in a series of videos in which I'm attempting to boot this Mini 803 from floppy disk. This is a machine I repaired in a previous series of videos, but at the time I wasn't able to boot it because I didn't have the boot disks. I've since been sent by a very kind gentleman what we now believe to be the proper boot disk for this machine. However, the machine is still refusing to boot, either directly from the physical floppy drive or from a floppy emulator. So what I've been doing is going through the basics of trying to find out why it's not working. So far what I've done is looked at the connection from the floppy drive controller to the disk drives, and also the voltage controlled oscillator circuit to see if that's responding to the data coming from the disk, which it is. In the previous video I showed that we were getting signals from the floppy drive. And so the next step really, because it's still not really trying to read the data from the disk, and I'll show you what I mean by that in a few minutes, the next step really is to start deciding how to go about fault finding on this. Now there are as many ways to do this as there are people that are likely to try it. You can use a scope, you can start swapping ICs out, you can use a multimeter to trace tracks. And what I want to do is show a technique I often use in a situation like this. It's not the only technique. I just want to show you the various methods that can be used. And what I'm going to do is use the logic analyzer to start investigating this problem from the code perspective. So that is, all the signals on a board like this are normally derived from the code that's running. Now once the operating system's installed from floppy drive, then that is mostly operating system creating the various activities within the electronics to fulfill the purpose of the unit. But at this stage, because the operating system isn't loaded, then all the activity is governed by the ROM, and the ROM contains the bootloader and the monitor program. So that's what we're going to be investigating in this video. We'll have a quick look at what is going on within the ROM code. If looking at logic analyzer screens is not your thing, then feel free to skip this video. It can get quite tedious. Just bear in mind that what I'm showing you might seem to take an awful long time, but once you're used to doing it, then literally each step I'm showing is just a few seconds. It will appear to take a lot longer because I'm moving the camera around and obviously waffling on about what I'm doing. But it is a very powerful technique for fault finding, and once you really get used to doing it, it's very quick and there is a lot of information you can get very quickly. And also it's fun. It's, if you want to learn about electronics, this is one of the best ways of doing that, looking at the combination of firmware activities and electronic behavior. And if you're into computer systems, whether they're old ones or vintage ones like this, this is a very powerful technique and a very interesting technique to use. One caveat with this technique is the inputs to the logic analyzer are optimized. So what you see on the analyzer screen is not always 100% indicative of what's going on the electronics. Just because the input to the analyzer is switching doesn't mean that the devices that are being fed by the line you're seeing switching are also switching. It could be there's a fault there somewhere, but again, this technique will allow you to track that down very quickly. So this will be quite a long video. As I say, if it's not your sort of thing, then feel free to skip it. But I've been asked to show this in some more detail, so that's what I'm going to do here. So the starting point is to get the code out of the ROM. So I previously showed this. This is the assembly listing. Ideally you want a full list file for the ROM, so I've produced a second file, which is this one. So I've also mapped the origin to what I believe is the origin of the ROM. I think it's mapped starting from F000. I don't have a schematic for this, and this is why this particular technique is being used here. Very powerful technique to use when you have no information about the system you're working on. So we have now all the addresses should be correct. They're not the address as seen by the ROM, of course, so if you're looking at the address on the ROM itself, then these will start at 0. But using these addresses and mapping it to the correct origin means that any jumps that are absolute within the code will show the correct address. And so in other words, this jump here is jumping to here, which is this address, and obviously that is correct. But we'll determine exactly where the errors are later on. Also, we've got the actual ASCII symbol showing in the center column. Not always particularly useful, but the reason they can be useful, I'll just find a part of the listing where it's good to have those. Okay, if we look at this part of the listing, we can see that when we look at the ASCII characters, then this is actual text. So these are not instructions, these are text strings that are stored within the system. Sometimes you'll get them appearing as instructions like this, and that's just because 2074 is a space followed by a lowercase t. So it is useful to have the ASCII characters showing so you can quickly determine if these are text strings or not. There's also a second useful reason for having these here, which I'll come back to in a few minutes. So once we have a starting point for this, the next thing is, well, how do we hook up the analyzer to actually make use of this? So first thing is we need two things as a minimum. One is the address, so we can determine where we are in the ROM, and the second one, of course, is the data bus, so we can actually see what the data value is that we're reading. So I'll get the analyzer started up and we'll start looking into tracing through this code. As I said, I will be going into a lot of detail with this video. I've been asked to show various things, including how the analyzer is set up. So going from start, we power up the analyzer, and what I tend to do is create a new working directory within the analyzer hard disk for each project, and I will save a separate configuration within that directory, and that means I can work on multiple projects. And if I ever come back to the machine again in the future, I'll already have the project to hand, and it saves me time setting up. The analyzer is actually very quick to set up. It looks like it's a very long and tedious process to set these up, but it's not. I think setting up this so far has taken, I guess, less than 10 minutes. But even so, it's still nice to have the setup to hand, if for no other reason than you can remember what you were doing. So firstly, we'll change to the directory that we want. So we select hard disk, and you'll get this screen, and this will show you the listing on the hard disk. And what we do now is we scroll down to the directory that our project is in. So in this case, it's Mimi 803. We go down to change directory, select, and we've now got that directory selected. Select the first file. You may have multiple configurations if you're doing different sorts of testing, and then select execute, and you can load the configuration. So 20 seconds and you've got your configuration loaded once it's all set up. And to show you what I've got so far, and this will change as we go through the fault finding process. So I've got pod 1, all 16 bits are connected to the address bus, and this is a Z80 processor in this machine, so it's a 16-bit address bus. The first 8 bits on pod 2 are connected to the data bus. Then have not read enable, A1 and A0, chip select, read clock, and raw data ROM chip select. I'll come back to what all these are used for as we use them, but the starting point is really to try to see if our mapping is correct for the start point of the file. So in other words, I want to see if we actually jump to here when the machine starts up, or when we try to boot from floppy drives. So we'll set a trigger point of F000 for the analyzer. So we'll go to trigger. As you can see, we've got F006. In fact, I'll set F006 instead. We could set 000, but what that does in theory is jump straight to F006. So I'll set F006 instead, set to that, so that will save us changing it. And I will also use chip select. So these values that we're looking for are in the ROM chip, and where we have the ROM_CS line, I've got it set here for 0. That means that when both the address bus is going to hit F006 and chip select goes low, then the analyzer will trigger. So in other words, when we try to read that address from the ROM, the analyzer should be triggered. So we'll go to waveform display on the analyzer, and now I will power up the MIMI, and you can see that we have indeed been triggered here. So we'll set to the trigger point, and you can see the address is indeed F006. And so if you're not familiar with the way the analyzer shows data, then the way I have this configured is the top yellow trace is the address bus. It's shown as a bus value, so it's showing us the value in hex of the 16-bit address bus. The blue trace is the 8-bit data bus, again shown as a bus value. And then we have the various signals. And the one we're interested in here is the green one. So we're triggering on F006. Notice it doesn't trigger straight away, but it does trigger as soon as the ROM chip select line goes low. So in other words, because these are both true at this point, then that's where it triggers. So what we've done here is we've triggered on an address of F006, and we know that the Z80 is currently enabling the ROM, and so the value put onto the data bus of 3E is what's coming from the ROM chip. If we look at the first page in the listing that we have, we can see that at F006 we should have a value of 3E, which is exactly what we've got. Moreover, we should see that the next address is 08. So if we scroll across, the next address that appears should be 08, and indeed it is 08. So notice that at F006, which is this first address, we're seeing 3E, and of course these address values increment, so although it's showing F008 here, then of course the 08 is at F007. So when we see F007, and again the ROM chip select line goes low to select that value, so in other words what's happening here is at F006 the Z80 is trying to access the data from the ROM chip, and it's reading 3E. It then moves on, address F007, and again it tries to read the ROM chip, and we're getting a 08 value. So it's reading 2 bytes from the ROM. The first one is 3E, which is correct, and the second one is 08, which is correct. So we can be fairly confident that we've got this set up correctly. So now that we have it set up correctly, the next question is where do we go from here? Okay, the next step really is to try and determine exactly how to go about tracing this code through. We know we can capture it, but we need to know how to make sense of it. So the real methods that you use are up to you. It kind of depends on what experience you have dealing with firmware, processors, and again, this doesn't really matter what processor type it is. It's just obviously what will be different is the instruction set, but the technique works equally well for all types. So what I tend to do is look for the out instructions. We know that if we look at the behavior of the machine itself, then one of the first things it's doing is writing text to the screen. So we know it writes text to the screen before it tries to access the floppy drive, and bear in mind what we're looking for here is the floppy drive block of code, but for interest what we'll do is just work our way through some of the simpler stuff. So the first thing is what address or what device is mapped at address 008H. If you're familiar with the Z80, you'll know that the out instructions all relate to addresses from 0 to FF. So we know that this is address 08, and the question is what's at that address, what's mapped to that address. There are various ways you can go about finding out. The easiest way is to have a chip select line that you can move around. In this case we've got a not chip select line, and just select it so you can see it more clearly. So that's this one, and if we select it you'll see that it's bit 11 on pod 2. So on the waveform display we can select that and insert it into our display, so it's this signal, and so now it's the signal at the bottom. And what we can do is we can attach that to the chip select line on the various devices on the board, and we can see if that coincides with the operation that we're seeing for the out instruction. There are other ways you could do this, of course. We've got the out line itself, but an easy way of doing this, because this will be decoded, so whatever's feed this is being fed to, it should in theory be decoded by the board. Could be there's a fault in that circuit, but again this is a technique that will highlight that. So the first thing we want to do is find out what is being accessed here. You could trace it through with a scope, of course, but what we're going to do here is make some assumptions, and I'm going to start attaching the chip select line to various chip select pins on the devices I think might be being accessed, and we'll see which one gives us a hit when we go to address F009. So it'll be 009 because that's the second part of the out instruction. So where I've decided to start with this is I've had a quick look at the board and seen what devices are on there. So what we know is happening at the startup is there's some information being written to the screen, and we must be configuring the floppy drive controller chip to enable the machine to try to boot from the floppy drive. So I would guess that either we are initially trying to access the floppy controller in this out instruction, or the CRT controller. What I've decided to do is make the assumption that the first thing it's going to configure is the floppy drive controller. The 08, I'm assuming, is the address of the floppy drive controller chip. I'll come back to why I think that's the case later on, but so what I've done to try and prove this is if we look at the spec sheet for the floppy drive controller, then we'll see there are various signals that are used to access it. We've got write enable, chip select, read enable, and then we've got these two lines labelled A0 and A1. If you look through the spec sheet, I won't show you the full spec sheet, so this video is going to get long enough as it is, but the A0 and A1 lines are used to select one of the 4 internal register sets, and depending on the combination of values on here, then you'll select one of those 4 registers, and whether we have the read enable active or the write enable active will determine whether we are reading from or writing to the selected register. And of course the chip select line is used to enable the overall chip. So what I've got hooked up now is the chip select line is going to chip select on this device. We've got write enable, so because it's an out instruction, I think we're probably going to be writing to this particular device. So I've got the write enables hooked up to this write enable, and the A0 and A1 lines are connected as a bus to the A1 A0 line, so that is a bus value, a 2-bit bus value. So what I'll do now is arm the analyzer and press the B key on the Mimi and see if we will capture something because the trigger's the same, but I want to see now what the action of the A1, A0 lines are. I believe they're being controlled through the out port of the Z80, and if we're correct, then when we get to the relevant instruction, so in this case when we get to the out instruction, which is at address F009, then we should see a value of 0808. So we're putting a value of 8 out onto port 8. Sounds a bit confusing, but if we look through the analyzer capture, then we'll see if that is the case. So the ones we're interested in here will use the yellow trace to find the correct location, which is address 09, and as you can see, we are indeed getting a value of 0808 on the address bus. So this is in fact the out. In this mode it's used as the out port, and we are putting out a value of 08, which is the blue trace, which is what we expect. So in other words, we're putting a data value of 8 out onto port 8. It's a bit confusing them being the same, but that's just a coincidence in this case. And if we look at the bottom two traces, then we can see that we are indeed writing a value of 8 to the register inside the floppy drive controller chip, which corresponds to address 00. So in other words, we've selected register based on a value of 00 on the A0 and A1 lines going into the floppy drive controller chip, and we're writing a value to the controller chip as we expect to. And what we'll do now is look into the spec sheet for the floppy drive controller and see what that particular register is, and if that value makes sense that we're writing to it. So as we can see, we're writing to address or register address 0 within the device, and we're sending it a value of 08. So if we grab the spec sheet for that floppy drive controller chip, there's a table in here that shows us what the two address lines select. We've got them set to 00, and so that is selecting the status register or the command register, depending on whether we are reading or writing. So we know that we are writing, so it's the command register, and if we then look at the table of commands, then we can see that what we're actually writing is a restore, or basically it's a reset, initialize a value to the register, which is exactly what we would expect the first byte written to be. So that's the general technique for looking through what we are doing with the actual hardware. So it does seem a bit complicated and cumbersome when you first start doing this, but it very quickly becomes second nature, and you can very quickly start to work your way through the code, find out exactly what does what, and it's, as I say, very straightforward, very easy. And once you've started going through with a particular machine, it also gives you a very good insight into the way the machine itself works. So earlier on I mentioned that it's useful having the ASCII code showing in the file. So what I would now normally do is just follow this through and find out exactly what's going on, and you can just follow the code through. You'll see it's incrementing, and you can see exactly what values are being written and read from the various devices. You can get a full memory map of all the hardware. To get the memory map, just go through, find all the instances of ins and outs. So we've got an in instruction down here, and so we could look at the address and see exactly what's being accessed at that address. So it's very quick and easy to do. But what I'll do now is, rather than bore you going through all that, because it will be tedious to do that on camera, but it is quite quick to do. The other sort of things you can do is if you look at various key addresses. So on the screen when this boots up, the top line is saying British Micro MIMI 803. So if we now look through the listing for that text, now the other thing to bear in mind is some ROMs it won't be in clear text. It could be encoded in some way, or it could be in a separate ROM. This is a very simple program, so everything's in a single ROM, so it's quite easy to follow through. So looking through the code, when we get to this page and this address, we see that we have these ASCII characters, and if you read down it says British, and on a single line we've got a space, so it's saying British space micro, if we go to the next page, micro mini 803, and that's exactly the text that appears on the top line of the display when this boots up. So what we know is somewhere in the boot sequence, before it starts to really read data from the disk, it outputs these characters to screen. So what we can do is start hunting through the code for this address. So we're looking for address F32B, which is the address of the first character, and we know that at some point this will be hit in a loop that's outputting data to the screen. And so if we search through, we can find the bit of code that's responsible for writing data out to the video memory. I won't do that here. If you want me to do that, then leave a comment. But this is the general technique I would use. We would then just start looking through the code. I would do a search through the file for that address. It might not be as straightforward as just looking for the address directly, because it's more than likely loaded into another register. Probably in the Z80 case, it's probably the HL register. It's often used as a pointer, and so what you might be looking for is the H and L registers being loaded with the 2 bytes that represent the address that you're looking for. But either way, it's normally fairly quick to find, and then what you can do is start looking for what each of these loops are actually doing. So you'll find that in here there will be calls to sub functions, and what you can do is start substituting the addresses for those calls and give them names. So if you find a loop, for example, that outputs a particular character to the video controller, then you can just change that address. So that you change this address and do a find and replace all for that address, and you would call it something like character out, and that would then start to make the entire file much more readable. And what you end up with once you've been through a few times is what almost amounts to the original source code. And then of course it becomes very easy to use this to fault find on the machine. And of course, if you know somebody else that's got one to fix, you can just give them the file and they've got the source code, and it really does help and makes fault finding that much more straightforward. Okay, now I have of course oversimplified all this, and it's one of the techniques that does require a bit of time and patience to get the best out of it. I mentioned that I knew that we weren't reading data from the floppy drive, and I'd explain how I knew that. So the way I went about checking this initially is, if we look back at the spec sheet for the floppy drive controller, we have this table that we looked at earlier as to what the A0 and A1 lines are for. And if we look at the bottom line, we can see that with the value of 1, 1 on those 2 lines, we've selected the data register. And of course, if we then read from the chip with these 2 lines set to 1, we're trying to read the data register. In other words, we're trying to read data that the floppy drive control system has read from the disk. So if we now go to the trigger and we change the trigger parameters, so we'll change this, we don't care about the address anymore, so we'll set that to don't care. And then we'll go across and we want to read from the floppy drive controller, which is this line, and it's active low, so we'll set that to low. And then the A0, A1 line, it needs to be 1, 1, which is a value of 3. And then any other lines we can select that will allow us to further determine exactly how to select that particular device and make sure we're not confusing the access to other devices. So again, chip select on that device, which is what that's connected to, is active low, and then we can just check to make sure that other lines we're not interested in are set to don't care. So in this case, we don't care about the ROM chip select line anymore, and all the other lines are set to don't care as well. So what we've got configured now is that when the machine tries to read a value from the data register on the floppy drive controller chip, then the analyzer will be triggered. So what I'll do is I'll boot up the Mimi, I'll arm the analyzer, and I'll press the B key on the MIMI, and as you can see nothing happens. And if the MIMI was ever trying to read data from the floppy drive controller chip, then of course the analyzer should be triggered. So that what we can see here is that although the floppy drive circuitry seems to be working to a certain extent, the machine is never trying to read a data byte from the floppy drive controller chip, and this is how I know that data is not getting out of the floppy drive control system. I mentioned in a previous video that the actual contents, the data contents of the floppy drive weren't important at that point because the machine isn't trying to even read them, and this is how I know it's not reading actual data. So this is what I'm investigating now. I'll go through the rest of the code. As I say, I've oversimplified this explanation, and it may well turn out that the addresses I've indicated here are not correct, but I'll sort these out as I go through. So the sorts of things I'll be looking for in order to properly determine the exact in-out addresses and the way that certain devices are accessed is to start looking through the code and developing a proper in-out map. In this case, for the floppy drive controller chip, we have this lookup table, so we know that we'll be looking for 4 addresses, and I have checked, and the A0 and A1 lines are actually connected through a buffer to the A0 and A1 lines on the Z80 bus, so we know that we'll be looking for 4 consecutive addresses. Also, some of these are both read and write, and again that's what we'll be looking for. We'll be searching through the code for a set of consecutive addresses with a base address. So for example, if the base address was 8, then the 4 addresses that we'd be looking for to access these registers would be at 8, 9, A and B, and that's what you could start looking for in the code. Now of course it's more than likely that they're used in registers as pointers, but again the registers have to be loaded from somewhere, and so you could still look for those addresses and trace it back from any in-out instructions that you find within the code. If you do want to see any more of this sort of thing, then let me know. I appreciate some people might find this sort of thing a bit tedious, but it is interesting, and as I say, it's a very good way to learn about these machines and to solve some otherwise quite difficult issues. I'll spend some time now going through the code, and if anything turns up I'll point it out in the next video, but hopefully we're getting closer to getting this machine to boot.